Hey guys, this is Garrett Wong, also known as Ensign Harry Kim from Star Trek Voyager, and you're watching Astronomy Live.
T minus 10, 9, 8, 7, 6, 5, 4, 3, 2, 1, 0. Stop.
Hi folks, sorry I'm late. I had a very embarrassing moment when I realized that for the last 30 minutes I've been streaming to nobody. Yeah, that's right. So, I had an old stream key in OBS, as it turned out. I didn't realize I had accidentally refreshed my stream key and it was no longer valid. And for whatever reason, OBS didn't tell me that I was streaming to the wrong key. So basically, the stream was going to Nowheresville. And fortunately, you guys didn't miss much. It was just me calibrating the camera, showing how I focused the telescope, calibrated the camera, and positioned it on M87, which contains a black hole. So, we're taking the first picture now of that galaxy containing the black hole, and we're going to see if we can find it here. So, again, apologies for the delay. Technical issues, my fault. I thought I was streaming, and I actually wasn't. So, I do want to point out that this is a charity stream on behalf of Exodus Road. You can find a link to donate in the video description. And so, in lieu of Super Chats tonight, please consider donating to Exodus Road. They do a lot of great work getting women and children out of human trafficking situations. They combat human trafficking. They go undercover to rescue people that are caught in those kinds of situations. They have teams in South America, India, and Thailand, coordinated by organizations here in the U.S. I had the chance to speak to the lead singer of Remedy Drive, and he and his band do a lot of fundraising and work with Exodus Road. And so if you check out this old video I did last year, I interviewed him. We were talking initially about an image that their band used as a cover photo for one of their albums, and it was noticed by some conspiracy theorists who thought that it meant that NASA was stealing images. In fact, the band was using a free image that NASA had taken, and they thought NASA had stolen it. Wasn't the case. Anyway, we got to talking about some of the charity work that the band does for Exodus Road, and I promised him that we would do some fundraising for that organization, and so here we are tonight doing a charity drive for them. So again, please don't send super chats tonight. Please consider instead donating to Exodus Road. If I receive any super chats from tonight will go to Exodus Road, but then YouTube gets a cut of it, and I'd prefer that not to happen. So I'd prefer everyone to just donate directly to the organization instead. So it looked like the autoguider was going a little bonkers there. The star might not have been quite bright enough. I'm going to try a slightly longer exposure to pull out this guide star. It's not the best, it's not the brightest, but it will hopefully do. There, that's a little better on the signal to noise ratio. Okay, let's restart this again. 5-minute exposure on M87, the black hole. So there's a supermassive black hole in M87. This was imaged by the Event Horizon Telescope, and you may have seen that in the news recently, using radio telescopes positioned all around the world, along with atomic clocks to precisely measure the time the data was received. They combined the radio waves received by telescopes in multiple countries all around the world to create what is effectively a telescope with the resolving power of a telescope the size of the Earth. Not the light-gathering ability, of course. That would require the telescope to actually be the size of the Earth. But The resolving power is also dictated by the size of your telescope, whether that's radio or optical. It's dictated by the size. Bigger is better. And although we may not be able to build a telescope the size of the Earth, we can combine the light from multiple telescopes in a process called interferometry. And this is called very long baseline interferometry. Not terribly creative, but that's because these telescopes are positioned all around the world with very long baselines between them. And you have to know their positions very precisely to do this, so it's quite an accomplishment. But they were able to collect this data and then use an algorithm to combine it to create these very high-resolution images, far higher in resolution than anything that you could achieve with regular size or individual telescopes, of course. And that's how they were able to directly resolve and take a picture of the event horizon and the accretion disk around it. And the resulting image matched very well with expectations, with simulations of what it should look like based on what we know of that galaxy and its central black hole. We hadn't been able to see that black hole directly before, or the event horizon directly before, but we can see a jet of material coming from that event horizon, coming from that black hole of material that failed to go into the event horizon but was instead kicked out and spewed out at relativistic speeds. And it produces a jet of material that you can actually see with much smaller telescopes, even amateur telescopes like mine. So that's what we're doing tonight. I've got the S-Big deep space camera. This is an S-Big ST2000 riding on an 8-inch LX200 Classic and with an A07 adaptive optics unit providing guidance. With this system, I should be able to start to resolve the jet of material that is being ejected from the center, from the nucleus of this galaxy by that black hole. And this is an elliptical galaxy 55 million light years away. That's this fuzzy thing you're seeing right here. This is a black and white image, of course. This was at half the resolution of the camera. And by bending those pixels together, you enhance the sensitivity so you can position things in the image before taking high-resolution pictures that require much longer exposures. This was just a few seconds, but we're doing now a 5-minute exposure at full resolution, where hopefully we'll start to be able to see the black hole jet. So that's what we're going for tonight. Of course, we're not going to be able to see the event horizon directly like they did. I don't have a telescope the size of the Earth, but I can hopefully see the jet of material coming from it. Some people have claimed that, I don't know, the image is fake or it's not a black hole, but the fact of the matter is it matches perfectly with predictions that were made. They didn't just look for something that looked like a black hole. Some people are suggesting that online, but that's not the case at all. They expected it to be there based on what we saw. We saw this material leaving this galaxy at relativistic speeds, being propelled by a very powerful gravity source, and that meant one thing: black hole. So, supermassive black hole at that. The Hubble Space Telescope, of course, has taken pictures of this galaxy before, and of course even Hubble is not nearly large enough to see the event horizon, but it of course saw this jet of material. And if you look at images that Hubble has taken over the years that it's been up, you can actually put them together and form an animation of how that material moves. I've actually done that before in an earlier video in some of my Hubble Highlights series. In one of those videos, I actually put those images together that Hubble's taken over the years and showed how that material is moving. And you can actually see that in the Hubble images, which is very unusual. I mean, most of the time, when you take images of galaxies over the years, you don't really see any motion visually, not by eye, not just by glancing at images. That's very abnormal. But it is the case here because this material is moving so fast, so close to the speed of light. So here we go, just 10 seconds left on this first exposure now of M87 at the full resolution of the camera. Adaptive optics units running. Things are looking good here. Let's see what this image looks like. It will have to take a dark frame. So it's gonna close the shutter now and take a 5-minute exposure with the shutter closed to take out all the noise. So all these colorful pixels here, these are just noisy pixels that are distracting us from the actual source. But if I scroll down here, yeah, I can already see it. This is fantastic. Right here is M87, and just off to the side we can see this slightly bluer streak here. It's hard to see, But that is going to be the black hole. Now, hopefully, when the dark exposure is completed, it'll subtract out that noise and it'll make the image a little bit better. And so all these colorful pixels here, these are not stars, these are just defective pixels of the camera. Every camera has them, but normally you don't see them on your typical consumer cameras. This camera, in some ways, is like a typical consumer camera. Every pixel is designated for a particular color, red, green, or blue. And there's twice as many green pixels as there are red and blue pixels. So it's a matrix of 4 pixels, 1 red, 1 blue, and 2 green, in a repeating pattern. And if any one of those pixels is defective, it produces this really bright color because it's just that one pixel. It's either a red, a green, or a blue pixel. And so the image has to go through processing to interpolate the completed full resolution image based on that data. But when you have a defective pixel that's reading all the way on, it produces this bright spot. But this image is very, very dim. I mean, these galaxies are extremely dim, even to a telescope like this. And this exposure has been running for 5 minutes, where the camera's just been on for 5 minutes. And you're pulling up the dimmest things you can out of that camera that's been exposing light for 5 minutes. So this is a very unusual situation. You wouldn't normally do this with a regular consumer camera, not with exposures this long. And if you did, most professional or even prosumer grade cameras, if they're like an SLR camera and they have a long exposure function where you can hold down the exposure for many minutes at a time, they'll have a long exposure noise correction system built in usually, and it'll do exactly what we're doing here. It'll close the shutter after it's taken the picture and take an equal exposure over the same length of time and subtract that from the image, and it'll do this automatically for you, similar to what's going on here. And when it does that, that's what it's doing. It's subtracting out the noise from all the hot pixels. So right now the camera's exposing for the next few minutes a dark frame with the shutter closed, and the only thing present in that image will be the hot pixels and noise in the image. And it will subtract that from this image and all other images it takes tonight to take out those hot pixels. Where in the States am I? I'm in Florida. Sorry, I'm having to look down here at my tablet for comments. One of the things I found about this camera, one of the quirks of it, is that if you pull up another window while it's taking a picture, it will ruin the picture for reasons I still don't understand. I just know that's what it does. And it seems to be a Windows 10 incompatibility. This camera is quite old. It was designed for Windows XP at best. But it's still a very nice camera. One of the things about it, other than the fact that it can interface with this adaptive optics unit, which is very nice, very powerful, is also the fact that it is actively thermoelectrically cooled. And currently it's at negative 10 degrees Celsius, and this is Florida. Obviously we're not freezing down here. But it's able to cool the CCD to these very cold temperatures to reduce the amount of noise in the image caused by heat. And so it's able to hold that temperature very precisely as well, which is important when you're doing a dark frame exposure like this, because temperature produces a background noise level. Other than the hot pixels, there's just a general glow in the image caused by heat of the CCD. And so as the temperature changes, if you have a CCD that doesn't control its temperature, that temperature will change over the course of the night, both from changes in the ambient air temperature and also as the CCD is running longer and longer, it'll tend to heat up more from the electronics that are running it. So if you don't have a CCD that's actively holding a set temperature, you need to take dark frames at every temperature the CCD was at, which is why your typical SLR will, for example, take a dark frame every single time it takes a picture if you've set it to do that, because the temperature is not necessarily going to be the same between any two pictures. And if you want a high precision calibration of the image, you need to know that the temperature was the same during the dark frame. In this case, the camera can directly hold a set temperature. Alright, so it completed the dark frame subtraction. We can now see a clearer image. You can see the bright yellow elliptical galaxy of M87, and this little thing sticking off of it, that is indeed the jet of material from its central supermassive black hole. So we're going to continue taking images here and collect, hopefully, a nice high-resolution image that I can stack and get good data on. The autoguider is going a little bonkers, probably because it was doing that 5-minute exposure and it's oscillating now quite badly. I might need to turn down the aggressiveness at which it's correcting. I don't know. We'll see. We'll see how this next picture comes out. If it's all streaky and stuff compared to this picture, then I'll do something to fix it. We can use the stars as a reference point. There's other dimmer galaxies in the field of view too, like this guy and this guy up here. These also appear to be probably elliptical galaxies close by to M87. According to Sky Safari Pro, there are a number of other galaxies in the field of view. For example, there's UGC 7652 that's within the circle defined by M87. I don't know, some of these might even be... I almost wonder if it's like, you know, halo galaxies and stuff. Well, okay, UGC 7652. I don't know where that is in the image here exactly, but it's 300 million light years away, much, much further than M87 at 55 million light years. But there's other galaxies here too. And that one's at 90 million. NGC 4486A is at 59 million light years versus M87's 55 million. I don't know, but I think that's up here. Oh, Red's Rhetoric just messaged me asking if I went in on a live stream talking about Falcon Heavy. Shoot, I need to tell him I'm busy. Where's my Skype? Get to it on my tablet here. Again, I can't pull up any windows on the computer while taking pictures. That's bad juju. You get weird anomalies in the picture. Actually, it's a very consistent anomaly. It's this bright sort of Venetian blinds effect across the image from pulling up other windows. It's very repeatable. Like, I can create it just by pulling up any other window in Windows. If I pull it up, it will ruin the image. So I just had a little pop-up window from Skype. I hope that doesn't mess up the image. No, don't update me right now. I should probably have signed out of Skype before I started the webcast. Sorry about that. We'll see. Hopefully it doesn't interfere. It was just a tiny little window, so maybe it'll be okay. Okay. Oh, hey. Huh. Oh, you know what that was? I bet that was the motor correcting or something. Oof. Okay, yeah, the autoguider went bonkers there. Go away, Skype. Go away. Yeah, I think that's probably going to have ruined the image. Maybe I need to recalibrate, or maybe I just need to adjust the aggressiveness of this guy. It probably wouldn't hurt to recalibrate. We are at a different declination than when I originally calibrated. That's usually not a good idea. That will potentially have effects on how well the guiding works. So I should probably just recalibrate the guider. We'll do that after this picture completes. It's only another 10 seconds. I think it's going to be pretty badly streaked by what just happened with the guider, and it's oscillating back and forth on trying to hold this guide star in the center. It's having a lot of trouble. I could probably tune it in just by reducing the gain, but yeah, look at that streaky picture. That's just awful. Ugh. Okay, we will fix this. We can fix it. So No. I was taking an auto guide picture with the main imager chip instead of the auto guider. There we go. Okay, let's go for 2 seconds. Just make sure it's bright enough that it can easily see it. Alright, recenter. Yeah, let's recenter the adaptive optics plate. Okay. And make sure we take out the slack. Okay. Let's calibrate the drive first. Let's see. Hopefully this doesn't throw the guide star completely out of the view. It's not going to be happy with me if it did. Nope. Okay, it's good. We're good. Okay, so it's going to move the guide star back and forth, up and down, and this helps it figure out how much it needs to move to center the guide star, and also the orientation of the camera as well. Okay, drive calibration successful, it says. So I need to adjust the drive calibration results here to make sure it's symmetrical about the y-axis because of slack in the gears. Okay, that's good. And then let's calibrate the adaptive optics unit. Okay, adaptive optics unit calibration successful. That looks good. We will try at full gain. We will try and just see what happens. I'm going to go for 0.7 seconds guiding exposure. We want it to be as fast as possible so it's able to respond to the atmosphere and everything else. Auto guide. Okay. That's reasonable. Okay, we will try another exposure here. 5 minutes. Go for it. The moon's starting to come up, but it's pretty far from where we're pointing, so it shouldn't affect things too much. The other night I actually did this. If you saw the preview pic, this really grainy black and white image, that was actually the same galaxy, but the moon was practically right next door. So there was a ton of moonlight, making it very hard to see at all. But I was able to just see the jet of material coming from M87, and that's what I highlighted with the red circle in the preview pic for this video, tonight's video. But now that the moon's a little further away and we've got a really clear night out, I wanted to take the opportunity here to do this. So again, if you're just joining us, I want to remind people, please don't send super chats tonight. Instead, consider donating to Exodus Road. They do work combating human trafficking around the world with undercover agents who are working to free people trapped in captivity, trapped in sex trade, and things like that. So please consider donating to them. It's for a good cause. If I do receive any super chats tonight, I will give it directly to them, but then YouTube takes their cut. I'd prefer not to do that and have to deal with that. So I would prefer people just donate directly to them tonight if you can. Thank you so much. Somebody asks, Jin asks, can you suggest a better finder scope situation for my Meade ETX 125? It's a good question. I guess it depends on the mounting bracket that's on the ETX. I don't know exactly what's on the ETX 125, but I do like a good red dot finder. I've got a red dot finder on my Nexstar 4-inch Nexstar SE, which is a pretty similar scope to the ETX line, and I find that works extremely well. So I like a good red dot finder. Some people prefer Telrads, these big blockier sort of holographic sight type devices. Neither of these have magnification, which is a hindrance if you're having to do star hopping and this kind of thing. But for day-to-day or night-to-night operations, and if you're just trying to find initial stars for aligning the scope, I prefer a non-magnified option like a red dot finder. So I'm not sure what the ETX 125 comes with. Maybe it comes with a red dot finder. I don't know. Maybe you're looking for something other than a red dot finder. But that's just what I prefer for most things, especially if you've got a scope that's got go-to capability. It's oscillating again. It's going squirrely on me. Okay. I'm going to stop taking the picture here. I'm going to abandon this picture for a second. And abort. Take image. What's going on here? Let's adaptive optics enable. Let's take the aggressiveness down by about half. Slew rate threshold. Let's increase that to 70% deflection. Bump size, tracking box, large. Okay. Let's center the AO. Okay. So I'm going to try to make it a little less squirrely, hopefully. Reducing the AO's aggressiveness will hopefully cause it to stop oscillating so badly. I don't know. Oh, it's still bouncing. Still bouncing on me. Let me exercise it a bit. Slew rate. Let's bring that down. Let's try this again. I don't know if that's really... I'm hoping that's just the adaptive optics unit just acting a little squirrely. Alternatively, it's the drives oscillating back and forth and the AO's not able to keep up with it. Yeesh, I hope that's not the case. I don't think it is. I'm pretty sure that's just the AO, the adaptive optics, bouncing back and forth, trying to overcorrect on either side. That's what it looks like, for sure. So I turned the aggressiveness and the slew rate way down. I don't know. May start to do it again. What's your big problem? Keep an eye on it. It's okay at the moment, but it was really bouncing all over the place there. We've recalibrated it, so that's not the problem. And it seemed to be working fine during the calibration process. But these systems are quite old. The AO7, geez, when did that come out? Probably That was well over 10 years ago, probably closer to 20 years ago. I don't know, somewhere between like 15 to 17 years ago, probably. I don't know. It's been quite a while. The A07 was like the original. Let's see. I'm curious now. September 23rd, 1998. Wow. Model A07 Adaptive Optics Unit, September 1997. Whew. Okay, it was over 20 years ago that this thing came out. So yeah, it's quite an old unit. Originally very expensive add-on for the S-Big camera line of the time. The S-Big that I have is the ST2000 XCM. This was one of the last cameras that would work with the A07. Newer cameras have newer adaptive optics unit systems that S-Big has made that will work with those cameras. But this works with the original, the A07, which is a tilt-tip mirror that can respond very quickly to atmospheric distortions and tracking errors to keep a guide star centered much faster than the telescope's own drive system could respond. When it works fantastic. And usually it works quite well. Normally it's not even possible for me to take pictures at the full f10 focal ratio, the full 2000 millimeter focal length of this telescope with deep space images like this. You can do lunar, planetary, short exposure images, no problem at this focal length. But when you're trying to guide an image for a 5-minute exposure and keep everything perfectly centered for 5 minutes straight, that's a very demanding task for a scope like this. This is a relatively affordable scope. The gears on it are not as fine. It's not as fine manufactured as some much higher price mounts that can cost even more than the price of my entire telescope just for the mount, in order to achieve maximum precision. So this device enables it to take much better photos than it normally would. And in terms of the readouts that it's giving me, the error numbers it's showing are not bad, actually. They're pretty reasonable right now. It's not crossing one. It's not going above 1 pixel error pretty much. It's staying at less than a pixel error in both X and Y axes. So it seems to be doing its job. Oh, there it crossed 1 pixel error in X. The X-axis seems to be where it's bouncing around the most right now, but it's okay. It's doing all right. I'm keeping a close eye on it. It's making me nervous because of how it was acting earlier. I always get nervous when this old equipment acts up because you never know when something's going to break down. This stuff's over 20 years old for the most part, so. Much better. Better than the previous picture, for sure. Some of you may be wondering about these dark circles. These are just dust motes on the CCD. These are taken out by doing flat field subtraction. These guys right here. So that'll be taken out in post-processing. Do I get much light pollution where I am? Not really. It's pretty dark here where I'm at. I'm pretty far from any major cities. So it's usually pretty dark out here. Tonight it's a little bit light out because we do have the moon coming up. So that's going to toss a lot of light out there. But on a moonless night, you can easily see the Milky Way. And it's pretty dark. It's not pristine or anything, but it's certainly dark enough for some serious deep space work. Could I explain what are adaptive optics? That's a good question. Probably should have covered that. So, adaptive optics are systems that are designed to compensate for the atmosphere, and they have to be able to respond very quickly to atmospheric distortions, changing turbulent atmospheric distortions. And so, there's different systems. Major professional observatories will often use a segmented telescope mirror, and each segment can be independently steered and tilted to deform the mirror, the overall shape of the mirror, to compensate for distortions in the waveform of light. And oftentimes those systems will use something like an artificial guide star. They'll shoot a high-powered laser into the air and image it and look at how that laser is distorted by the atmosphere in order to produce their own guide star and be able to very precisely correct for the atmosphere. This is, of course, not as high-tech as that, but it is a tilt-tip mirror that acts kind of like a star diagonal. If you ever see a star diagonal on your telescope, it diverts the light 90 degrees into an eyepiece or a camera. And, sorry, I think I just got a text or something. So, it will divert the light into the camera. But it's on a tilt mechanism that basically tilts the mirror at high speed in various directions in order to change the light path. And it looks at how the guide star is moving and tries to correct it so that it keeps it centered throughout the exposure. And yeah, that's basically what this is. It's a tilt-tip mirror system. And oftentimes, even the more professional systems that involve deformable mirrors will potentially have a tilt-tip mirror system on top of that in order to correct for overall shift of the image caused by the atmosphere. It's going wobble again. It shouldn't be calling in the drive system. I'm looking at, so I've got it set to, I think, 70% tilt is where it calls for help from the telescope's drive system. That can cause it to wobble a bit. The drives are not as accurate as the tilt-tip mirror system. But I don't think it should. Well, okay, at that point, yeah, there it should have asked for help from the drive. It's just now hitting that point. So, the tilt-tip mirror system has limits. It can only tilt a certain number of degrees, right? It's actually a very small range of degrees. I don't know exactly what it is, but it's a pretty small range that it can tilt. Once it reaches close to the limits, it has to call upon the telescope to move its drives to recenter the star closer to where the mirror can keep up with it. So it's really a coordinated effort between the camera and its adaptive optics system and the drives as well. Okay, that came out pretty good. That came out reasonably well. The stars look pretty round there, not too streaked or anything. So it seems like it's working. It's working well. So if I zoom out, the overall picture actually looks more like this. So you can see some larger dark circles. This is probably dust, possibly on the adaptive optics unit itself. I did clean it the other day, or attempted to clean it the other day. It could also be dust instead of on the CCD directly. There's also a quartz window into the CCD chamber that might be affecting things as well. But yeah, there's definitely the black hole jet sticking out here from the galaxy. You can see it there. It's a little hard to see in this image. I don't have control over the contrast of the color images from the camera, although theoretically this is supposed to be able to control contrast. It can only do it for black and white images. If I go to grayscale, do I risk it? I don't know. I'm always a little nervous about pulling up any additional windows while it's taking a picture, because it has the potential to do the Venetian blinds thing and ruin the picture. I used to think that the camera was having a problem, that the camera was actually dying. I actually bought a replacement camera because I thought the camera was dying from what I was seeing. All these elevated light levels in the image, where you get like half the image that's like way too bright and then half of it that's too dark. And I thought it was the camera, the CCD, having trouble, so I bought a replacement identical CCD, and it had the same problem. Come to find out, it's not the CCD, it's me. It's whenever I pull up a window. It's a Windows 10 incompatibility. This software, the CCD soft, is not officially supported anymore. It's not updated anymore, and it was not really designed for Windows Vista, Windows 10, or anything like that. I forget when they stopped supporting it, but it was really built for Windows XP, and the new fancy UI of Windows 10 does not play nice with it. And somehow it feeds back into the camera. I don't know how, but it does. So I can't pull up any other windows, which is irritating because I would like to make a grayscale copy of this and play with the histogram a bit. But even if I pull up a window within this program, it could potentially affect the image. Don't really feel too keen about doing that. I mean, these are 5-minute exposures. It would be a shame to waste the time on an image that I ruined because I was too impatient. I pulled up another window. But at the end here, when we're done collecting images, I will process them for you guys real quick and do a quick and dirty processing just to show you a higher quality view of what this looks like, because it is adjusting the contrast automatically here, and it isn't doing the best job necessarily. These are high bit depth images, so these are 16-bit images. Your typical monitor and my monitor can only display 8-bit images natively, and so it's having to basically crunch down on the histogram and just focus on a particular portion of the histogram, the brightness values of the image, in order to show you, the dimmer parts of the image, and it's washing out some of the brighter parts of the image. That's why the galaxy just sort of looks like this blob, this featureless blob. I mean, it's an elliptical galaxy. Elliptical galaxies, to me, all are kind of featureless blobs, but there should be better detail there than there is. And particularly in that black hole jet, I think there's going to be some more detail to be seen there, particularly when I stack the images, but also just handling them myself in terms of the contrast of the images. I could probably pull out some more detail that we are not able to see at the moment. So when we're done here, I will do a quick and dirty stack of the images and process them so we can take a higher quality look at the black hole jet here. So this is again M87. This is the same galaxy that scientists using the Event Horizon Telescope first took a picture of a supermassive black hole. It was at the center of this galaxy, and that's the same black hole that's producing this jet coming out of it right here. So it's pretty cool stuff to be able to see evidence of that same black hole here with an amateur telescope from my own yard. I mean, that's why I love astronomy. Anyone can do it. Anyone can get involved with it. You don't have to have the world's most impressive equipment to start to see some of these things. Oh, and you might have noticed there was a bright couple pixels down here that suddenly went away. That's characteristic of a cosmic ray strike. Random bits of radiation hitting the CCD from space, that will trigger charge buildup in those pixels, and it will be registered as bright pixels in the image. But it's actually from radiation particles hitting the CCD, inducing a charge temporarily. The file format is FITS, F-I-T-S. So this is a standard raw file format used by astronomical CCDs at anything from Hubble Space Telescope right down to my humble S-Big camera. And this is a raw file format that can hold images that are high bit depth, like these 16-bit images. So you have to normally do some tone mapping or something to translate them into 8-bit images that most monitors can display, and in formats like JPEG, for example. Those are 8-bit images. So, yeah, and also, this is a single-shot color camera, so the color filters are built into the pixels here, red, green, and blue pixels. The grayscale version of this camera that doesn't have those color filters over the pixels is actually a little bit pricier than the one I have. It's actually worth a little bit more because astronomers generally prefer not to have single-shot color cameras. They generally prefer to have grayscale cameras where they can put their own filters and do things like narrowband imaging, like you see those beautiful Hubble shots, Hubble Space Telescope shots. Oftentimes they're taken using narrowband filters that look at very specific wavelengths of light corresponding to emissions of different types of atoms, different ionization levels of different elements. And so they can actually analyze the composition of a nebula or a galaxy using those filters. But for that, they need to make sure that they have a grayscale camera, because otherwise you're just wasting tons and tons of pixels and time. For instance, if I put a hydrogen alpha filter in front of my camera, I could do that and look at a very specific emission line of the hydrogen in a nebula, for example. But that will only allow red light through it, a very specific red light wavelength. And so 2/3 of my pixels, and actually more than that, 3/4 of my pixels are not going to be used, the green and the blue pixels. The camera is actually made up of a matrix of 2 green, 1 blue, and 1 red pixel in a repeating pattern. So if you're only using the red pixels on the camera, you're missing out on 3/4 of the pixels. 3/4 of your pixels are doing absolutely nothing. And so you're just killing the resolution of the camera by pre-filtering the colors to produce a single-shot color camera, which is why the grayscale version is actually a little more valuable for astronomers. But this is a single-shot color, this is true color, similar to what your eye would see, except it is also sensitive to infrared light. And I am getting some serious bouncing of the camera. Whoa, hey, we just lost the guide star altogether there. It bounced right out. What's going on there? Okay, I think the tilt... Let's abort the image. That would have streaked it all to heck. I think the tilt got too high, and I think part of the problem... Calibration time, drive calibration results, I think part of the problem it's not letting me. It's probably because I got the AO attached. It's like it doesn't let me set relay bump size. I don't know. It seemed like before it helped when I increased that a bit. Okay, let me reset it. It was definitely at the stage where it would have been calling for help from the drive system to recenter the star a bit. And that may have created an issue if the drive was being kind of wonky about it. It would help if I could guide at a faster rate. In fact, I might even try that. It's probably a bad idea, but I'll try it anyway. Let's try 0.5 seconds. Try to guide a little faster, hopefully not deal with as much crazy oscillations of it. We shall see. He was doing well there for most of that image. Oh, yeah. So Jen says she loves super close-up images of the sun with a hydrogen alpha filter, and those hydrogen alpha photos of the sun are usually taken at a very narrow wavelength, using very specialized filters, not just the kind you slap on a deep space camera, but filters that you can actually tune. Uh, because believe it or not, um, even the redshift and blue shift of the sun's rotation is enough to start to see that when you tune a hydrogen alpha filter for one side of the sun or the other, depending on if it's rotating towards you or away from you. It's enough to shift the frequency of that light a little bit, and you can bring it out a little bit better by tuning to the side of the sun you're looking at, that kind of thing. And so some of those filters are really, really narrow, and there's actually a new product out there now I'm kind of interested in getting in the future if I can ever afford it. It would be the Quark Eyepiece, which you can use with standard refractor telescopes, off-the-shelf refractors that weren't necessarily designed for solar observing, small wide-field refractors or things like that, little 60 to 80 millimeter refractors. Bigger than that, it gets to be too dangerous, too much sunlight is concentrated on it. And normally I would say stay far, far away from any solar filter that claims to be an eyepiece solar filter. That's dangerous. And even here I would say don't do this unless you really know what you're doing with solar observing. But it's pretty cool because you could take even a simple achromat that's relatively cheap and isn't well color corrected. And here it doesn't matter because you're only looking at one specific color of light. It doesn't matter if there's chromatic aberration and would cause color fringing because there's only one color you're looking at, so there is no fringing. As long as you focus that very specific wavelength, you're in perfect focus. The fact that it's an achromat is irrelevant. So pretty cool stuff that allows you to get some high quality images with scopes you may already have laying around. So that's something I'd like to acquire in the future for sure. But not a cheap accessory by any means. I think it's north of $1,000 just for that eyepiece. And it's the same story for most hydrogen alpha scopes that are of any quality. Alright, I'm going to zoom out a little bit. We got 1 minute left on this exposure. I'm going to zoom out a little bit and just take a look at the stars as the picture comes in. Hopefully the stars are nice and tight. Keep an eye on the auto-guiding settings. Only 5 seconds left on this exposure. Okay, good. Now it did shift a bit because I reset the position of the tilt tip mirror system there. That came out well. I just think that maybe the issue is when it hits 70% tilt, then we start to get issues because at that point it calls on the drive system to kick in and recenter it, and it seems like it's having trouble working well at that point. It's actually kind of chilly out here tonight. I'm going to go get a jacket. I'll be right back. I stumbled back to my chair. How are we doing here? Looking pretty good? So far, so good. Though we're reaching that point in the tilt of the adaptive optics that we ran into trouble last time. Let's see what happens. So, for people joining, I want to say again that this stream is a charity stream for the Exodus Road. Exodus Road is a search and rescue organization that fights human trafficking around the world, with undercover teams in South America, India, and Thailand fighting to rescue people out of human trafficking situations. So you can donate a one-time donation or even a monthly donation to help them out and help them fight and combat human trafficking around the world. Their teams also include social workers who provide immediate care to survivors in recovery. And they do really important work. So in lieu of Super Chats tonight, please give them a donation. The link is in the video description. So, hope everyone had a happy Easter. And I thank you all for those who have donated already. Now we're reaching 80% tilt. It should be calling on the mount to correct that, but there's slack in the drives, and if it's having issues, if it's not taking out the slack fast enough, that could be the reason why it's getting bouncy as it approaches the limits of the tilt to correct. So there's a manual fix to this problem, which is simply to stop the exposure after this picture and manually recenter the tilt. So as soon as this picture is done, I will do that. 1 second. Okay, so that picture came out good. Let's just recenter the AO. Okay. And restart guiding. Okay. And now we'll take the next picture. Well, that's one way to fix that problem. I think it's a problem with the slack in the gears. It's called backlash. It's particularly prominent in the declination axis. It's either that or the relay's not working. That's possible. Well, no. No, it's not. I know it was working because I tested it earlier. If it wasn't working, then I couldn't have done the guiding on the scope. I couldn't have done the drive calibration. So the relay has to be working. It's just got to be the backlash. I also know I set the limit higher for when it would kick on the motors, in case that was causing the oscillations. But it should have kicked on by that point. At 80% for sure, it should have kicked on. Yeah, as far as I can tell, it wasn't kicking on. Now, if there's backlash and it's still working its way on taking out the slack on the backlash, then you won't notice. It'll seem like it's not doing anything. But we're at pretty good values here. The stars are nice and round, real sharp. So I think things are working well, both with the focus and with the guiding. Obviously got some stars that are a bit brighter here, but these fainter stars look really pretty tight. So I'm quite happy about that. This window a bit bigger. Move this out of the way. Get that up there. Okay. So, if anyone's joining recently, I haven't pointed it out in a while, but this is the black hole jet sticking off the side of the galaxy here. It's a little hard to see, but it is slightly bluer than the galaxy. It'll be easier to see, I think, once I process these pictures properly with some stacking and manual processing of the contrast. These are high bit depth images, and what we're looking at is just a portion of the histogram, which is why the galaxy core itself looks fairly featureless. We aren't quite overexposing anything, whether the stars or the galaxy. It's actually falling within the range of the histogram by a little bit. The maximum pixel value, as you can see on the camera control window down here, for the main imager is 64,641. That's just under the max limit of the camera. If you hit a value over like 65, it's like 65,000 whatever, then yeah, at that point you are exceeding the max, or you're overexposing something. You're maxing out the maximum brightness the camera can perceive. And these brightness values don't extend from 0 to 255 like a normal 8-bit image. These are 16-bit images, and so the brightness values extend over a range of about 0 to, if my math is right, 65,025 would be the max value. It's 255 times 255 for a 16-bit image. So, the camera's capable of producing high dynamic range images. You may have seen HDR labeled on some newer TVs now. That's starting to be a thing that TV manufacturers are focusing on, is improving the dynamic range of their TVs to better create the vast difference in contrast that we experience in real life between things that are dark to things that are very bright. And that is defined as dynamic range. Now, even a camera like this only has a tiny portion of the dynamic range of our eyes. Our eyes are very good, actually, at seeing things across a very wide range of brightness values. Oh, that image came out real sharp. That's really good. Really, really good there. Yeah, our eyes are much better at perceiving wide ranges of brightness than most cameras. So, for example, if you take a picture of the moon, which is rising at my location right now, I can see it through the trees coming up. If I were to take a picture of the moon, I wouldn't see any stars around the moon if I set the camera to properly expose the bright lit surface of the moon. And yet, I can look at the moon and, I mean, there aren't too many bright stars around it from what I can see. It's in the trees still for me. But, yeah, if I look off in the corner of my eye, I can see a bright star. What is that? Yeah. Anyway, I can see a bright star off in the east, to the left, way to the left of the moon. I can see a bright star over there with my eye, but the camera wouldn't be able to do that. Our eyes perceive light in a more logarithmic fashion, which is why the magnitude scale in astronomy is logarithmic. So if you look at the magnitude scale, it's logarithmic because that corresponds to our eyes. When the astronomical magnitude scale was first established, it wasn't quite the same as it is now, but it was basically similar. It was human astronomers looking at stars saying this star is one magnitude brighter, or twice as bright, and really it's a logarithmic scale. Because that's how the human eye responds to light, whereas cameras like this, CCDs, respond to light in a much more linear fashion. And because of that, they can't cover nearly as much dynamic range, even a 16-bit camera like this. And so, these images I'm taking now pretty much span the full dynamic range of this camera, between the very bright stars and the very dimmest faint galaxies and things like that. M87 is a fairly bright galaxy, but there's some dimmer galaxies like this little guy up here. This looks to be probably a dim and very distant galaxy, pretty much at the limit of the camera's ability to detect, compared to the more bright objects like the stars in the galaxy, the main galaxy, M87. But by taking multiple exposures over a period of time, you can basically stack them and get a higher signal-to-noise ratio than you could from an individual image. Yeah, I don't know, actually. Now that I think about it, I cranked up the relay limit to where it would call on the telescope to move things back into center at 70%, or maybe I even cranked it up to 80% of maximum tilt. I think it was 70% of max tilt, but the way it displays these values is tilt 50% is actually centered. So 70% is only basically 75. You get to about halfway to maximum tilt. That's not 70% of maximum tilt. So yeah, I probably would have had to get to about 85% max tilt before it called on the relays to fire up the telescope motors incorrect. So I'll have to keep that in mind and see if I can let it run out that far next time. See what happens. We were having issues earlier with it oscillating quite badly, the guide star, and I'm not sure if that was because the auto guide or the adaptive optics unit was set too aggressively, It's possible. Or if the motors were being kicked on and causing it to wobble about. It's working good now, though, so I'm not going to look the gift horse in the mouth. I'm just going to take it for what it is and get as many pictures as I can with it working. I did make some adjustments, though, to the aggressiveness of the adaptive optics unit to tame it a little bit, hopefully. So if you guys have any other questions in the chat, just let me know. I'd be glad to answer. I'm just noticing now so I've set the camera to be negative 10 degrees Celsius on the CCD. I can specify how cold I want it to get, and it uses thermoelectric cooling to chill the CCD. And I'm only at 50% power on that chiller. I could actually run it colder if I wanted to. Probably a lot colder on tonight. I had a cold front move through, so it's a fair bit chilly out. I could probably drop this thing to negative 15, maybe even negative 20 Celsius. Not going to do that, though. That would require recalibrating with a new dark frame. Don't necessarily want to do that, but I have to keep that in mind for next time when it's this chilly out. I can cool this thing a fair bit more. Like I said, though, when we get done here tonight, I will go ahead and process these images to reveal just how much we can see in the stacked, processed final image. Which I might actually do here soon. We're coming up on 1 a.m., so I am going to have to bring the webcast to a close pretty soon. In fact, I'll probably stop the imaging here for a moment and just assess how many images I've actually got collected at this point. downloading that image. It came out pretty good. Okay, we're going to abort taking the picture for the next one. And I'm going to open up the directory here. See, again, I can't open up any windows while I'm taking a picture because it will ruin the picture, because Windows 10. Weirdness. That's not good. Autosave on. Oh. Oh. Gave myself quite a scare. I opened up the directory. There's no images because I was saving in the wrong directory. That's okay. I can easily move them over to the correct directory. And let's go ahead and change the autosave location to the correct directory. Alright. Scared me to death. So we have 11 images so far. 12 images will make it a full hour, solid hour of light. I'm just going to do a very quick and dirty deep sky stack here. Open up my deep sky stacker software and dump in the light frames. Let's set this to color images. Set the interpolation, because the red, green, and blue pixels have to be interpolated into color pixels. Okay, and actually, okay, one of these images was ruined by bad tracking. The others are all pretty good. But I do want to see if I can collect a good 10 minutes of light. I'm just going to do a very quick stack here and just take a look at where we're at on the quality of the image we can expect to see here. Ooh, that looks pretty nice. Yeah, alright. Well, let me just go ahead before we collect the final images, because I've already gone and done this part. It won't take very much here to actually just adjust the contrast of the stacked image and just show you guys how much we've collected so far. So excluding the one image near the beginning that got ruined by bad tracking, we have 10 images to work with. And those 10 images do produce a pretty nice looking picture of the jet. So I'm not going to do anything too fancy in terms of processing, not really proper tone mapping here, just adjusting the brightness and contrast a bit to be reasonable. Oops. Let's adjust that a little downward like that. Oh yeah, I like that. I like that a lot. That's pretty cool. Okay, let me share this window. Hopefully this will work. Actually, you know what? That won't work. I remember that doesn't work. I've done this before. I've been down this road before. It didn't work. I'll just save it as a JPEG. Like that. Okay. Now let me see if I can load this up. Image. Okay. Let's go get that image. Okay, I saved it as just a regular JPEG after processing the brightness and contrast of it. Cool. Alright, there it is. So I haven't processed for dark or for flat field subtraction or anything like that. So you do have these donuts here. I'm going to try to blow the image up a good bit so you can see there in the center, of course, is M87, is the golden looking galaxy, but there's also this blue jet within the galaxy that you can see right there. That is the jet from the black hole, from just 10 minutes, 50 minutes worth of light. 10 images, 50 minutes worth of light. While you guys are looking at that, I will go ahead and close down PixInsight and Deep Sky Stacker for the moment. Save the file list under M87. And close that. Okay, and so now I'm going to go ahead and resume taking pictures. I'll let you guys enjoy that picture here for a bit while I resume taking images. So we're going to take 10 more minutes of light here. Center AO. I'm going to take 10 more minutes of light and then call it a night. I just want to round it off to a nice even hour's worth of light collected. Alright, I've resumed the image taking, so I'm gonna let the camera work on that. Let the telescope work on that. And yeah, I don't think that's too bad for just 50 minutes of light. You can very clearly see the jet coming off to the right there in the galaxy. And you can even see the tint of it is quite different than the rest of the galaxy. You can see how it's bluish. So yeah, again, the Event Horizon Telescope was looking at this very same black hole at the center of this very same galaxy. The supermassive black hole producing that jet is what they were taking a picture of. So that's why they knew to look for it there. They saw this jet coming from this galaxy. And as galaxies go, it's relatively close. It's 55 million light years away, which, sure, that's a big distance, but there's a lot of galaxies that are a lot farther away. We don't have any quasars nearby that we can take a look at. But this galaxy was obviously containing a supermassive black hole that's quite active and spewing out this material from this jet. So that's why they knew to look for it, because it must be a fairly large black hole to produce a jet like that, and it must be fairly active to produce a jet like that. And so they looked towards the center of where that jet's coming from in this galaxy with the Event Horizon Telescope, and sure enough, they found it. They found the black hole. with its accretion disk around it, and it's a monster. It really is a monster. That event horizon that they found in that image, if you superimposed our solar system into that image, it would fit within that dark shadow of the event horizon. The Voyager 1 probe would just be at the edge of where that event horizon is in the image. So it's rather huge. And of course, I can't see that, even as big as it is, at 55 million light years. You're talking, tiny, tiny, tiny fractions of an arc second in size. One arc second is 1/3,600th of a degree. And the image that you're looking at right now, the pixels, the individual pixels, are, maybe, what are we looking at here? We're looking at probably 0.7. I'm going to say probably around 0.7 arc seconds per pixel at best. And, the black hole, its angular size is, thousands of times smaller than that. And so you need a massive amount of resolving power from a telescope that is effectively as large as the Earth in terms of its resolving capability. That is the point of the very long baseline interferometry, the combination of multiple radio telescopes to produce that kind of resolution. So, yeah, even to do this, of course, we've got the adaptive optics unit on here to maximize my telescope's capabilities. Being able to actually do deep space imaging at the full focal length, 2,000 millimeter, 2 meter focal length of this telescope, in order to maximize the amount of resolution you get, and be able to correct for the atmosphere even, to some extent, with this adaptive optics unit. Running 2 corrections per second to keep this star centered and get these high resolution images. But even this is not a silver bullet for basic fundamentals of amateur astronomy, things like polar alignment. You will still get field rotation even with an adaptive optics unit if you haven't properly aligned the scope. So that's why I did a tutorial last night showing how to do a polar alignment, the way I do it at least, using the iterative method, capitalizing on the telescope's slewing and go-to capabilities to align on the north celestial pole, align the axis of the telescope perpendicular to the axis of Earth's rotation. And so to do that, you have to be able to see the stars, see Polaris, slew to Polaris, the North Star, and center it up, physically center it up with the mount based on where the telescope expects the North Star to be. Then you slew over to a distant star somewhere near the celestial equator, separated by a good amount in both right ascension and declination from the North Star. Then you center that up with the motors and sync to it with the telescope's computer. And then you slew back to Polaris and correct for the mount's pointing error. And you bounce back and forth like that. I did that a couple times tonight at the start. And even that I would call a fairly casual polar alignment. I only did a couple iterations, but it was still far more accurate than anything I could have done just by eyeballing it. It's not good enough for doing this kind of high-precision astronomy. If you really want to eliminate field rotation as a factor, you have to do that. You can't just eyeball and say, well, it's pointed where I see north should be, and according to the dial on the wedge or on the mount, it's at my latitude, so good enough. No, that's not really good enough. When I powered on the scope and slewed to Polaris, Polaris wasn't even in the eyepiece. Okay, I had to reposition the mount a fair bit to get it in the eyepiece, because the eyepiece is only going to show me, a small, tiny portion of the sky. The moon will fill that eyepiece, even my widest field eyepiece, with this telescope. And so it's not accurate enough just by eyeballing it to get it in there. I had to do a fair bit of adjustment, finally got Polaris in the eyepiece, put in a crosshair reticle eyepiece, centered up Polaris by moving the mount around till it was centered on Polaris, and then moved over to my second star, which in this case was Regulus, and bounced back and forth between Regulus and Polaris, alternating between aligning the computer and where it thought it was pointing to where it was actually pointing, and aligning the mount to be closer and closer to true north, to be able to be aligned parallel to Earth's axis of rotation. And that's really what you have to do for this kind of work. So the moon's coming up now, and there's been talk lately on other channels about field rotation being abnormal, or that there's some abnormal rotation of the moon on top of field rotation, perhaps more subtle. Fact of the matter is you have to do a very accurate polar alignment if you want to completely eliminate field rotation. Furthermore, if you are adjusting your camera between recording videos of the moon, if you're adjusting the zoom, the magnification, and then you start recording again and suddenly the moon is shifted, odds are that's your fault. Odds are you bumped the camera. To confirm that you didn't bump the camera, you would have to go back and point at the North Celestial Pole. You could do this after you were done observing the moon for the night. Slew the telescope back to the North Celestial Pole and stop the motors. Take a star streak photo. Let the star streak over 5-10 minutes and just produce some partial star streaks where we can see concentric circles coming from the stars centered around the North Celestial Pole. That will be at the center of these concentric circles of star trails, because you're pointing at the North Celestial Pole, in theory. Then you move the telescope in right ascension with it set to be 90 degrees declination. So move it to 90 degrees declination with the motors, and then rotate it in right ascension while taking a second long exposure. So this one can be just a few seconds long, really. You just need to move it in right ascension, at a reasonable slew speed, so that you produce artificial star trails caused by you moving the telescope. If you are accurately polar aligned, the artificial star trail photo should overlap with the natural star trail photo. They should have the same center point of those concentric circles. If they don't, then that means you bumped the telescope, and it is out of alignment. And that's why the moon appeared to rotate dramatically all at once. So, believe it or not, that's actually a thing that is being discussed right now on a couple of channels. So, yeah, that's how you do that. If you want to prove that your alignment actually was accurate and that you didn't bump the telescope, you can do that by taking star trail photos. It can be a useful tool. I've done it before, and you can see that on the live stream I did of the supermoon a couple months back. Alright, so we've got picture number 2 in. So now I have a full hour's worth of light to process. I'm going to take one more for good measure, because that first picture, it was not quite as sharp, I think, as some of these latest pictures are. So gonna take one more just for good measure, because we've got good weather here. As we go into summer, we're going to have less good weather nights here in Florida, so want to take advantage of this as much as possible. We're at 75%, 76% tilt in the y-axis. So I don't know if it'll come out streaky. I know I've been staying on that still image. It's a higher quality image than these live images. But we'll have an even higher quality still image here by a little bit here in a minute after I get this final picture down. So yeah, this is really cool to me, to be able to see direct evidence of the same black hole that humans were able to take a picture of directly for the first time, able to actually see the event horizon in the accretion disk. That is so cool that they were able to do that, and to me it's really cool that even an amateur astronomer like me can take a picture of the jet coming from that black hole in its galaxy, in this case the elliptical galaxy M87. So it is possible in theory to actually see this in the eyepiece. I don't know so much with this size telescope. I think you need a larger telescope to actually see this by eye. You know, this camera is taking these 5-minute long exposures. It's collecting light for 5 minutes. Our eyes don't work like that. Our eyes process the light immediately. They don't build up light and then show us what's there. So even with well dark adapted night vision looking into the eyepiece, I don't think you could directly see it. Now, if you had a night vision eyepiece that was image intensification, what they call image intensification eyepieces, which is just like the kind of night vision that the military uses, only adapted into an eyepiece that you put in a telescope. If you use something like that, then yeah, you could probably see it. But just using a regular eyepiece and looking in a telescope like this, I think you need a larger scope, but it has been done. It has actually been seen in some larger scopes. But that's the advantage of doing deep sky photography like this with a high quality CCD camera. We can see things much dimmer than what our eyes can see, even with the help of the telescope. But when you're doing these long exposures, it is very demanding. You need a good accurate polar alignment and preferably some high accuracy auto guiding, unless your mount is extremely expensive. This LX200 Classic used to be considered a luxury telescope. I mean, top of the line. These days, there are a number of mounts frequently used by amateurs that are a lot more luxury than this thing, a lot more expensive and a lot higher in accuracy in terms of their ability to track without even auto-guiding. But those are much more expensive than this entire setup put together, pretty much, in some cases. Things like high-end astrophysics mounts, plane wave telescopes typically go on those kinds of things, you know, these really expensive Ritchie-creations and all this crazy stuff. This is just an 8-inch LX200 Classic, but the cool thing is that with this adaptive optics unit, with the A07, it punches above its weight. It's able to take these pictures at very long focal lengths that would, I think, shock a lot of amateur astronomers who are used to working with higher-end equipment. Granted, they don't have to go to these kinds of lengths to get, you know, highly accurately tracked photos. They do have to still polar align very accurately, but the mounts will naturally tend to track without nearly as much what they call periodic error, which is sort of this wobbling back and forth, where it will track accurately over periods of time, but it will undergo cycling of stars wobbling back and forth, caused by the gears not being perfectly round. Okay. Alright, I'm going to call that good. So I'm going to stop taking pictures, and I'm going to fire up Deep Sky Stacker one more time. And I'm going to open the file list that we had before. Okay, we were up to image number 18, or index 18 at least. Where is it? I'm going to go back into the directory. No, I want to view this as a list. Okay. Sort by type. Oh, no, Alright, that's fine. I had set it to save the registered images separately. I shouldn't have done that. I don't really need that right now. Okay, so 20, 21, 22. Now we've got 13 light frames. Yeah, okay. So, stacking parameters, alignment, intermediate files, turn that off. Light, averaging, sure. Okay, it's stacking the light frames now. Okay, now I need to go into Pixin's site and process that. Actually, let's do this the right way. Let me do some proper tone mapping here and do a proper HDR, high dynamic range image. Treat this like the high dynamic range image it is, and adjust the contrast properly. So I'm going to save this as a TIFF, a high bit depth TIFF file, 16-bit, and then go into Iris and tone map this thing. So tone mapping is basically an algorithm that will take this high bit depth image and translate it into a low bit depth image in a way that preserves the contrast, the variations in intensity in the image. Let's see. Graphics, TIFF. Okay. Oh yeah, that looks quite nice. Okay, we're gonna do a reduce HDR command to call this 0.5, 0.5. How's that look? Reasonable. Man, the color saturation there is a little extreme. Made it look really red, the whole image pretty much. I don't know, let's see how this looks. I may or may not like this. Though there's also the possibility of getting real fancy and save one, Iris. There's a possibility of getting real fancy and basically layering the color from the standard def or standard dynamic range image onto the HDR image if I don't like the color intensity, I guess, the color saturation. I don't know. Let's see what happens here. Okay, let me adjust the contrast. There's some uncorrected hot pixels there. They'll be easy enough to process out later on. Let me do dynamic background subtraction to clear out variations in the... Get a little bit of vignetting from the light cone being choked a bit. Try that one more time. I don't want to sample the light from M87. I just wanted to generate the background light without that. Okay, that's better-ish. I can do better than that. Come on. It's sampling the galaxy's light. Don't want it to do that. Okay, let's try that. That's better. Okay. General pixel math. Subtract the background light. So now I'm going to subtract modeling of the background light to flatten the contrast in the image. That looks nice. Okay. And now we do a final curves adjust to it. Yeah, that looks pretty nice. It looks pretty nice. Alright, so I'm going to save this now as a JPEG image. And then we'll load that up. Okay, cool. So, let me add the new image. And there we go. So there's some uncorrected hot pixels here and there. And so I'll correct those manually later. But for now, let me just zoom in on M87 here. And you guys can see the galaxy with the jet coming from its central supermassive black hole. Cool beans. Let me zoom in a little more. Come on, you can do more than that. There we go. That's what I'm talking about. So you can see the elliptical galaxy there, M87, and then off to the right is this little bit of bluish material. That is the jet coming from its central supermassive black hole. We did it. We found it. So not too shabby, I'd say. And that's true color. Basically, it's also including some infrared and UV light that the camera is sensitive to that our eyes are not, but they are normal colors here. The pixels are red, green, and blue filtered just like any other consumer digital camera. It just doesn't have the infrared blocking or UV blocking filters over it. So yeah. So again, thank you all for watching, and again, if you would consider donating to the Exodus Road, they're rescuing people in human trafficking situations around the world, ranging from South America to India and Thailand, and they need your help. So please consider making a donation tonight, and hope you all had a very happy Easter. Thank you for watching. I'll be processing a better version of this picture, hopefully a better version, taking some flat field images to calibrate for the dust motes on the CCD, and get a final image processed, and I'll upload that to the video description later as well. Alright, thanks again for watching. Clear skies, folks.